Hey everybody, wanted to go through AP 2010 AB-3 with you. So have your paper ready to score it, and I'll show you how the scoring guide works and to give you some other hints and tips and tricks. So let's take a look. All right. So this is the amusement park ride. We're 700 people in line waiting for a popular amusement park ride. The ride begins in operation in the morning. Once it begins operation, the ride accepts passengers until the park closes 8 hours later. While there's a line, people move onto the ride at a rate of 800 people per hour, and the graph above shows the rate R of t at which people arrive at the ride throughout the day. Time t is measured in hours from the time the ride begins. So looking at my work over here on the right, the graph itself, R of t, is the rate at which people arrive. So I'm thinking rate. This is a derivative graph. So this is pouring in. And the other rate involved in this problem is that there's 800 people per hour getting onto the ride once they're in the line. That is the dump rate, and that's a constant rate. So I gave it a name. I called it M of t for moving. So that's the rate at which people move into the ride. So this is a pour and dump problem. So let's see what the questions that they're asking us are. How many people arrive at the ride between 0 and 3? So arriving at the ride, the rate is R of t, so that's this graph. So we want to find the area underneath of it. Area underneath a people per hour graph in terms of hours would be the number of people. So that's what they're calculating over here. Integrating the graph represents the area under the curve. Then we're going to find the area of two trapezoids and get a total. Now, 1 point is just for literally writing the integral on your paper. So integral from 0 to 3 of R of t dt, so give yourself a point. And then the other point is calculating now, they broke it up and I broke it up into two trapezoids. 1/2 sum of the bases times the height, 1/2 sum of the bases times the height, and that's 3,200 people. You do not need to add up 3,200 people. You can literally leave the expression, all of this, like we've shown before, and leave that. So you don't have to do anything there. Now, in the end, you might want that number for a later part of the problem, but we'll get to that. So 2 points for number part A. Part B, is the number of people waiting in line to get to the ride increasing or decreasing between times 2 and 3, and justify your answer. Well, their description here on the scoring guide I don't think does a really great job of what you could be doing. The number of people waiting in line is increasing because the people moving onto the ride at a rate of 800 people per hour, that's M of t, my M of t. And from 2 to 3, the rate of people getting into the line is more than 800. So if you look at the graph, between 2 and 3, the rate at which people get onto the ride is between 800 and 1,200. So therefore, the people are getting into the line at a greater rate than people are getting onto the ride. So therefore, the line is getting longer. So over here on the right, you can see that's what my description here above is doing what they had done on the scoring guide. M of t is constant, R of t is greater than 800, so therefore M of t is less than R of t, so therefore the number of people waiting in line is increasing. Now, in a pour and dump problem, sometimes you might want to make a total rate equation. So I called T of t the total rate of people waiting in line. And that's a difference of the two rates, the rates of people getting in the line and the rate of people leaving the line and getting onto the ride, R of t minus M of t. Well, again, these are rates, these are derivatives. So I want to know when I'm getting is the number of people waiting in line increasing or decreasing? Well, I just need to see what the rate is doing. Is the rate a positive rate or is a negative rate? And overall, T of t, my overall rate, is going to be positive. R of t is more than 800, M of t is 800, so therefore this is going to be a positive number, so therefore the number of people waiting in the line is increasing. Didn't have to do it this way, but I'll show you later on how that might come in handy, doing this overall rate idea. Part C, at what time is the ride the longest? How many people are in line at that time? Okay, if you're looking for when the ride's the longest, you're looking for a maximum. And how do you find maximums? Well, you set the derivative equal to 0. Well, that's what I did. Let me show you what I did first. So to setting the derivative, the overall derivative, the rate in this whole problem, which is T of t, I set it equal to 0. And in order for T of t to equal 0, R of t and M of t must be equal to each other. And that is when at time 3. At time 3, R of t is 800, so it's this point of quote-unquote equilibrium. When the rate of people coming into the line and the rate of people getting onto the ride are exactly the same. Well, we got to see what was happening before and after. So I, again, for my overall rate problem, my T of t, I made a T of t number line and I checked. Before, basically back when I was between 2 and 3, I knew that R of t was greater than M of t, so T of t was positive. I used this information back here to say that this was positive. Then afterwards, my R of t is going to be less than 800, so I knew that was going to be negative. Positive to negative for a rate equation, since T of t changes from positive to negative, and I defined T of t earlier, I can say I have a max. The other way of doing this is just saying, okay, between 0 and 3, R of t is greater than 800. Between 3 and 8, R of t is less than 800, so therefore it's a max. It's going from positive to negative, or greater than and less than. So in terms of points, you get a point for identifying T of 3. T equals 3, the rate when the rates were both equal. And, oh, I guess we didn't get to the point where and the justification is a point, and we didn't get to finding the number of people in line. Well, you started out with 700 people. Hopefully you didn't miss that at the very beginning of the problem. Then 3,200 people arrived during this time interval from 2 to 3. From 0 to 3, I should say. That was back in part A, so that 3,200, I did actually need that at this point. And then during the 3 hours from 0 to 3, 800 people per hour got onto the ride. So there's my minus 2,400 to get a final of 1,500. Do you have to have 1,500? Nope, you can just have this calculation right here. And that's your number of people in line solution point. Then the last thing, write but don't solve an integral. An equation involving an integral expression of R, whose solution gives the earliest time when there's no longer a line for the ride. Well, really, that's kind of based upon back what you did in part C. So back in part C, you were figuring out what the total number of people in the line was. Well, I want the total to be 0. I don't want anybody in the line. So I'm going to set, oh, and I didn't do it on my paper here. Ugh. I'm going to put a big equals 0 here. So that's not an equation, I wrote an expression. So I need an equation. So I started out with 700 people. I accumulated during T hours. So they said at time T in this problem. So 0 to T of R of X, I made up some new variable, R of X dx, that's the people getting into the line, minus 800T, the number of people that got into the ride during those T hours. Basically exactly what I was doing right up here. And then I have to set it equal to 0. So 800T was a point, writing the integral is a point, and then the final answer, which includes the fact that you've got the 700 and the equals 0, is another point as well. So there you go. There's your 9 points. So go back and go backwards through this video if you need to re-see something again. My work again is right here. And then make sure that you go on to my form and fill out what score you're giving yourself in the end. All right, thanks.